few things, but let's try it.
Okay, go ahead.
All right, so I am going to talk about the public-private versus, well, one way of doing symmetric cryptography, and first, one way of doing symmetric cryptography. I can hear myself.
Wait, no, somebody, there must be, somebody,
Oh, sorry. Anyway, so yeah, first I'm going to talk about modulo, which we've covered, but it is the remainder of an integer division. So, for example, well, this is an example. And two numbers that have the same modulo are congruent, like, well, these two. And this is really useful because you can apply modulo at several points of many calculations. For example, for an addition, you can do it on each argument or at the end. That's also true for multiplication, and really, really, really useful. It is also true for exponentiation. And that means that if you want to calculate really the exponents of really big numbers, it will maybe still be a lot of work, but it will not take a gigantic amount of memory. So you can have a huge number to the power of another huge number. Here, huge means a few hundred bits, but it'll still be a possible amount of memory. And so modular exponentiation allows here for cryptography. So public-private key, similar to your example. Imagine a contact in the crowd, and this crowd is allegory for the internet. The only way to pass things is to pass things through the crowd. And you want to contact someone deep in the crowd, and you cannot, and you want it to be confidential. So you cannot use a cipher because anybody will be able to read the cipher. You cannot pass a key, you cannot pass anything like that. What you can pass is, on the one hand, an open padlock, and you keep a key, and they match. So you send the padlock that's open, and with the padlock, in reality, both of these things would be, in practice, numbers. The other people cannot do anything. So the person can put the message in a box and send it back to you locked, and you have the key. And you can make, since it's numbers, as many padlocks as you want. So that's how RAS works. I'm not really going to cover it because I don't have much time, but one thing is that, as we saw, the key, for some reason I find silly, is called the private key, which is silly because all keys are private. And the padlock is called a public key, which is also silly because no key is public. But anyway, then what if we want to encrypt and decrypt things to each other? And so we put like something inside of another cipher? Well, we don't need to do that. We can actually keep a number in common without exchanging anything private. Let's say we have here represented as a common paint two numbers, and then an extra number that is unique to us. We can then mix our numbers and exchange the mix. Because this is done through exponentiation, the numbers cannot be unmixed. And then if we mix the numbers with our original number, we have a common number. And here is an example with small numbers. And if I had Prep at the beginning, I would go into more detail. But anyway, you can see that through exponentiation, with only exchanging, we have the original modulus and base. We exchange the mixed numbers, which here are 10 or 11, and we both get 14. And that can be our cipher, which in reality would be a huge number.
All right. Well, that's time, and I think that's fine. Thank you.